presentation, we shall briefly look at few examples of non-normal or abnormal or supernormal mode oscillations that we can routinely see in spring mass systems. But if we attempt to solve the Newtonian force balance equations, we would never get solutions covering these non-normal modes. Newton's method gives only a very limited subset of all possible solutions. The solutions can all be well ordered and numbered according to the increasing frequency value. The solutions given by force balance equations are called the normal mode solutions. In a 2-spring 3-mass system shown here, the top two configurations show the normal mode solutions. Normal mode solutions are discrete, and there are a finite number of such solutions for a given system. For the 2-spring 3-mass system, we get only two valid normal modes. This is the normal mode 1 here, which has lower frequency, and normal mode 2 has relatively higher frequency for the same given net energy value of the system. The bottom examples show some configurations outside the list of normal mode solutions. They exist in reality, but are not captured by Newton's equations. We can partially describe them by using net energy conservation equation and the net linear momentum calculated when all the springs are relaxed. Because we don't find the whole complete momentum when the springs are strained. Because when the springs are strained, some energy and momentum is locked up within the springs. And when the springs are relaxed, the masses will have the entire energy and momentum available to them. So we can calculate the net momentum properly when all the springs are relaxed. That information, that is the information about the net energy and linear momentum of the system, is carried by the amplitude and frequency of oscillation. The global or the net energy and momentum conservation equations cover the entire continuous spectrum of all possible solutions, but the Newtonian equations give only a very small subset of all these possible solutions. Let us first recall what happens in an elastic collision. In the simplest case, we can assume that the two objects have the same mass. Suppose m1 and m2 have the same mass m. Initially, the two objects are at rest. We disturb only the first mass with some velocity v meters per second, and the second mass remains at rest. So m1 starts moving right with an uniform velocity and eventually collides with mass m2. After collision, m1 transfers its entire energy and momentum to m2, since m1 equal to m2 is same as m. m1 and m2 have the same mass m. So the energy and momentum is transferred entirely from m1 to m2. So after collision, m1 stops and m2 starts moving with velocity v meters per second, same as m1 in the first step. For simplicity, we shall mostly stick to interactions between all equal masses in this presentation. So after collision, we see m1 is stationary at the place where the collision happened, and m2 is somewhere on the right, moving with v meters per second. This collision is fully described by the energy and momentum conservation equations. So this is the momentum equation, and this is the net energy equation. There are no potential energy components, just the kinetic energy. When m1 and m2 have the same mass, m, the energy and momentum equations get simplified to this form. v1 plus v2 equals v, and v1 square plus v2 square equals v square. And from this we get the solutions V1 can be either V or 0, and when V1 is V, V2 becomes 0, and when V1 is 0, V2 will be V meters per second. So these are we get two sets of solutions. So these are them. So if before collision m1 was moving with V meters per second and m2 was at rest, then after collision m1 will be at rest and m2 will be moving with V meters per second. So that is, after the collision, the velocity states flip from one possible solution to the another possible solution. Similarly, a one spring two mass system where m1 and m2 are connected to each other using a spring will constantly flip between these two above states. That is, the velocity states v1, v2, representing the velocities of masses m1 and m2. So this ordered pair v1, v2 goes like v, 0 and 0, v and v, 0. That is, in the first step, m1 had velocity v and m2 was at rest 0. So it flips to 0v. So m1 gets rest and m2 is moving with velocity v, and then it flips to v0 and 0v and so on. First, m1 collides with m2, transferring all its energy and momentum. Then m2 collides with m1, transferring all its energy and momentum back to m1. Then again m1 collides with m2, and so on. Since the two masses are connected by a spring, they are in a sense confined with respect to each other and keep colliding with each other over and over again. And whenever the spring is relaxed, we see one of these states, these before and after states, that we get from elastic collision calculations. And the states keep flipping between these two options, before and after. And so we shall see this process in more detail now. Suppose initially the spring mass system is relaxed and at rest. We disturb the first mass m1 with a certain velocity. The spring starts compressing from the left. Only m1 is moving and m2 is at rest. Eventually m1 comes to rest and the compression stops. The spring is compressed with less length L minus C at this stage, in the step 2 here. And m2 is triggered into motion at this stage. Energy and momentum possessed by m1 is transferred to m2 via the spring, connecting spring. So m1 remains at rest in stage 2 and after that. This step were shown here. So this also implies that the one spring two mass system gradually keeps shifting right. So we shall see that. Between the second and the fourth steps here, m2 moves right while m1 remains at rest. So in the first step m1 was moving. In the second step m2 comes to rest and m2 is triggered into motion, and in the second, third and the fourth step we see m2 moving. In step 3, when the spring length becomes L, so in the step 2 the spring was compressed to the maximum extent, it had length L minus C, it started expanding from that. So now in step 3 it has reached the length L. So this is the relaxed length. So it does not have any stored potential energy. Therefore, we see m2 moving with the same velocity as m1 in step 1. So m2 now has the same velocity as the input velocity m1 we gave in the first step. So m2 continues to move right when the spring length becomes L plus C. So the spring has expanded to the maximum extent possible. The expansion stops. The whole energy is stored as potential now. There is no kinetic energy. So m2 comes to rest, and at this point m1 is triggered back into motion. So m2 stops now, and it's like m2 has collided with m1 and transferring all its energy and momentum to m1 through the spring. So m1 starts moving right now. So M2 stops and M1 starts moving right. And M2 remains at rest after step 4. In step 4, the spring which has length L plus C starts compressing from left. And by step 5, the spring length is back to the relaxed length L. So this step 5 configuration is same as in the step 1, but the whole system is shifted right, translated. And the configurations in step 3, 4, 2, 3, 4, these steps will be repeated below the step 5 because it's a repetition. The steps 1, 2, 3, 4 keep repeating over and over again and translating to the right. The shift rightwards is because of the non-zero linear momentum in the system given initially. The amplitude of the oscillations given by this ordered pair C1, C2 switch between C0. So C0 is what the oscillation we see between step 1 and 2. And it switches between C0 and 0C. So in the first step, only the first mass M1 is moving, so it has the amplitude C, and the second mass is not moving, so it has amplitude 0. So that is the amplitudes of the simple harmonic motion that the two masses have. And this switches, in step 2, this switches from C0 to 0C. That is, now the mass M1 is at rest, it comes to it stops, so the amplitude is 0. And the second mass is oscillating at this stage, is getting into the oscillation, so it has the same amplitude as C1 before in the previous step. So C0 switches to 0C. So, and these are the states corresponding to the two elastic collision velocities that we calculated. So V1, V2 solutions we got was V0 or 0V. So either one of the masses will have all the energy and momentum at in one state, in the before state or after state. So that way the energy and momentum keeps shifting between mass M1 and M2, and the whole system keeps shifting rightward. For half the period, only M1 is moving or oscillating with amplitude C, and which shows a maximum velocity V. And during this half period, M2 remains at rest when M1 is moving. And then for the next half period, only M2 is moving and M1 remains at rest during this period. So alternately M1 and M2 moves. The energy gets localized and the momentum gets localized in M1 for half a period and M2 for half a period. We get these configurations as a solution to the energy equation here, and along with the assumption x2 is equal to alpha x1, where alpha is some proportionality constant between these two variables x2 and x1, which represent the position of the masses. So we get sinusoidal solutions from this energy equation based on this assumption x2 equals alpha x1. Even without this assumption we can get, but for in cases where there are more number of masses, this assumption works really well. So in any case we get these sinusoidal solutions as shown here. So x1 oscillates with some amplitude c1 and x2 oscillates with some amplitude c2, and they have a common frequency omega. The amplitude and frequency we get from the equations in the previous slide are such that they satisfy the global momentum equation, which can be written in a simpler way as m1 c1 omega plus m2 c2 omega equals p, where p is the momentum. And also they satisfy the energy equation. So basically m1 c1 square omega square plus m2 c2 square omega square is twice the energy. So these are the momentum and energy equations in terms of this variable c1, the amplitude of the variation of the oscillation. So the whole math has been explained in detail in a previous video, so I'll not go into the details here. So please check that video on our YouTube Neofizix channel. So what we described in the previous slides was an example of a non-normal mode where only one of the mass in the one spring two mass system is disturbed as an initial condition. So initially we disturb only one mass of this two masses connected by a spring. But Newton's equations do not allow such an initial condition configuration. So according to these Newtonian calculations, what we get the normal mode, this is not one of the normal modes, so it is not allowed. This kind of oscillation is not allowed by these force equations. So we get the normal modes as a solution to the force balance equations. This is the force balance equation for M1 and this is for M2. We could assume x2 equals alpha x1 for simplicity, same as in the energy case. So x2 equals alpha x1. Or we could solve in a different way and still get these two sinusoidal solutions in a longer way. So the key point here is this ratio alpha or this ratio C2 by C1. So alpha equals C2 by C1, so these are the same. So this ratio alpha or this ratio C2 by C1 should have one particular value minus M1 by M2. So this is the only value allowed according to the Newtonian equations, these force balance equations. So alpha has to be, or C2 by C1 has to be minus M1 by M2. So in our case, we have used M1 is same as M2 and they both have the same mass M. So in this case we get alpha equals minus 1 or C2 by C1 equals minus 1. Hence the two disturbing initial velocities must be equal and opposite. So if we disturb M1 with some velocity v, we have to disturb the M2 mass with velocity minus v, equal magnitude but opposite direction. So this is the only initial condition allowed in the normal mode solutions. But for this one spring two mass system. But in reality, the two masses can get disturbed with any arbitrary velocity value. And we need to figure out how the system responds under all those arbitrary conditions. So the force balance equation two mass system. But in reality, the two masses can get disturbed with any arbitrary velocity value. And we need to figure out how the system responds under all those arbitrary conditions. So the force balance equation gives only this kind of motion that is valid for this two spring one mass system, one spring two mass system. But this is not the only kind of disturbance that this system experiences. The masses can get some random arbitrary velocities v1 and v2 as the input. So how will this system behave under those conditions? That's what we have to figure out. So let us just put the normal mode and one of the abnormal modes that we discussed earlier, where only one mass is disturbed initially. So this normal mode, both the masses have to be disturbed, and in this abnormal mode that we have discussed, only one mass of this two mass one spring system that we have disturbed. So we'll put them side by side for comparison. On the left is the normal mode solution. This is the only possible configuration that we get from the Newtonian equations for the one spring two mass system. On the right is one of the infinite possible configurations from the non-normal mode solutions. So non-normal mode has infinite solutions. This normal mode has only one solution given here. Here in the non-normal mode, here only one of the masses is disturbed as initial conditions. This is one particular non-normal mode solution of the infinite possible, and here we are considering that only one of the masses, this M1, is disturbed, M2 is at rest. So this is not a normal mode basically. Newtonian equations cannot analyze this or do not get this as a solution when we solve these force balance equations. One of the glaring differences is between these two is that in the normal mode solution, the center of mass of the system remains stationary as the net momentum is zero. The normal mode solution are those elastic collisions with net zero linear momentum, while the other solution can encompass both zero and non-zero momentum. What we should notice is that we cannot tackle all kinds of input disturbances just by using the normal mode calculations. Is that we cannot tackle all kinds of input disturbances just by using the normal mode calculations. This may be a very significant point. So this is an animated version of the comparison between a non-normal mode and the normal mode one spring two mass system. So on top is the non-normal mode, and we see that the energy moves back and forth between the first mass and the second mass. So it keeps exchanging between the first mass and the second mass, the energy and momentum. And in the bottom we see the normal mode. There is no transfer of energy between masses. Every time the springs are relaxed, M1 and M2 will have the same individual kinetic energy. If we take M1 and M2 as two different masses and we solve that, then we see M1, if it had some velocity v1, it will remain v1 whenever the spring is relaxed. It doesn't exchange with M2. So that is how this animation looks. One of the best illustration of this non-normal mode in real world comes from the numerous videos of the Slinkies walking down a road or walking down a treadmill, walking down a stairway, etc. This behavior cannot be explained merely by using force balance equations, and it involves a net non-zero linear momentum like in the non-normal mode that we discussed a few slides ago. So basically it will have a net linear moment. It's not stationary at a position and oscillating. The both sides are not oscillating. It moves in a certain direction with the given initial linear momentum that is conserved, and it shows. It gradually shifts, translates. But the energy conservation and momentum conservation are only two equations. So they can describe two mass interactions in a well-defined manner, because we will have two variables, C1 and C2, and two equations. So it's a neat system. Two variables and two equations. It can be solved in a well-defined manner. For more than two masses, these two equations do not form a well-defined set. In case of three masses interacting, we can possibly use the conservation of frequency as another or the third equation. It's a necessary equation. These two equations are not sufficient. Thus the momentum and energy equations are not sufficient. So we need a third equation. So at best we can describe a two spring three mass system using these three equations: the energy, momentum and frequency conservation. So this is the system of equations, and let us look at an example involving a two spring three mass system. So consider a two spring three mass system or 2s3m system. Initially the springs are relaxed and the masses are at rest. We disturbed only the second mass in the first step. So only this middle mass in red, orange, only that has been disturbed with some velocity v. The second mass m2 moves to the right, compressing the second spring and expanding the first. The amplitudes of this oscillation are C1, C2, C3 equals 0, C0. So it indicates M1 and M3 are at rest, only M2 is moving and it has some amplitude C. In the second step, M2 comes to rest after the second spring has got compressed and this first has got expanded. All the energy gets stored in these compression and expanded springs. M2 comes to rest, and the first spring is expanded to length L plus C, and the second spring is compressed to length L minus C at this stage. So at this stage now the amplitudes switch from the value 0C0 that we saw in the first step, in the second step it switches from 0C0 to 2C by 3 minus C by 3 and 2C by 3. So the amplitudes are all less than C, and it has 2/3 the amplitude of the original. The M1 and M3 have the same amplitude in the same and same phase oscillation, and M2 has the opposite. So it's so if M1 and M3 are moving to the right, M3 is moving to the left. So in this case, the first spring starts compressing from this relaxed length. In the third step, they would be relaxed. In the second step, basically, this is expanded, this is compressed. So the first spring which is expanded starts compressing, and the second spring which is compressed starts expanding. So in the third step, both the springs are relaxed. So it has expanded. The compressed portion has got expanded to length from L minus C to L, and the expanded portion has got compressed from L plus C to L. So both the springs are relaxed in this stage, in the third step. And M1 and M3 are moving right with velocity 2v by 3, while M2 is moving left with the velocity v by 3. So v1, v2, v3 will be 2v by 3 minus v by 3 and 2v by 3. So this corresponds to C1, C2, C3 values that we saw in the previous slide. So the first spring continues getting compressed between the second and the fourth step. So it's continuously compressing from second step onward till fourth step, and the second spring keeps expanding in the same from step 2 to step 4. So the masses come to rest when the first spring length becomes L minus C. From L plus C, it becomes L minus C, gets compressed. And the second spring is now expanded. From L minus C, it becomes L plus C in the step 4. So at this stage, the movement of all three masses stop. All the kinetic energy is converted into potential energy of the spring. So the amplitudes again switch now from 2C by 3 minus C by 3, 2C by 3 back to 0C0. So it will keep switching between these two, 0C0 to these 2C by 3 minus C by 3, these values, and then again back to 0C0. So now it has switched in the fourth step. It has switched from these 2C by 3 minus C by 3, 2C by 3 back to 0C0. So in this case, only the second mass starts moving, while that is M2 gets triggered into motion, and M1 and M3, they will remain at rest. So only M2 is moving in step 4. So by step 5, we see that both the springs are back to their lengths L, original relaxed length L, and the middle mass is moving with the maximum possible velocity V. So this configuration is same as whatever in the fifth step is same as that configuration that we see in the step 1. Only difference is the whole system has shifted right. It has translated to the right. That's the only difference. Otherwise, fifth step is the same as step 1. It has got repeated. And below this, all these second, third, fourth steps repeat. So these steps 1 to 4, they keep repeating forever. So the two spring three mass system discussed in the previous slide is qualitatively same as the one spring two mass system shown here. That is, the middle mass M in the two spring three mass system is interacting with the total 2m mass at the edges, and this can be reduced to a system with two masses such that there is one mass M and there is another mass twice this 2m connected via a single spring. So these two are sort of equivalent. The velocities we get and the amplitudes we get are similar. So the two spring three mass system is kind of reducible to the one spring two mass system with elastic collision between these two masses. So this can be reduced to this. and these two masses systems is easy to analyze using these elastic collision equations. So it is easy to solve this, even this system with three masses. So this is a special case that can be solved. It's three masses, and we have the three equations with frequency conservation along with energy and momentum conservation. Most other cases will not be reducible like this. So before looking at such cases, let us check out the normal modes of this two spring three mass system. So this is the normal mode 1. The net momentum at any time in these normal modes will be 0. So even in the relaxed state, the linear momentum will be 0, should be. So in order to excite this mode, we have to disturb the first and the third masses with opposite velocities, but with the same magnitude. So if m1 has velocity v, m3 must have velocity minus v, so that the net momentum is 0 of the system. And the middle mass will remain at rest forever. It never moves. No matter what the state of m1 and m3 is, m2 remains at rest in this mode. So the amplitudes of this motion, the amplitude C1, C2, C3 forever remains C, 0 and minus C. In this mode, it will never change. It will not switch from this set of amplitudes to another. It remains forever C, 0, minus C. So C and minus C indicate that they have this opposite phase. M1 and M3 have opposite phase, and this 0 for C2, it implies that mass 2 is not moving, it is at rest. So this is one of the two solutions we get by solving Newtonian equations for the two spring three mass system. And this is normal mode 2. So this is the other solution we get by solving the Newtonian equations for this two spring three mass system. So the net momentum is again 0 and the center of mass remains stationary. So in order to excite this mode, we have to disturb the first and the third masses with the same velocity. Same phase, same direction, same velocity, v and v. So m1 and m3 should have the same velocity, same magnitude, same direction. And the middle mass should have twice this velocity, but in the opposite direction. So the middle mass will have, if m1 and m3 has velocity v, the middle mass m2 should have velocity minus 2v. Should have velocity in the opposite direction. This also means that the middle mass should have twice the amplitude of m1. So they'll have one common frequency, and if these m1 and m3 velocities are v, their amplitude corresponding will be, say, c, then the amplitude corresponding to the motion of m2 will be 2c. So that is what we see. So the amplitude c1, c2, c3 forever remains c minus 2c and c. So this gives the amplitudes of the oscillation. So not all input disturbances will have these forms required by the normal modes. So the normal modes, there are only two possible shapes. If something is other than this, then these equations cannot. The Newtonian equations fail to capture their motion. So now let us move to configurations which are not reducible to equivalent two-body elastic collisions. Let us consider the same two-spring three-mass system that we discussed earlier, but this time in the initial condition we just disturb one of the edge masses. For example, say we disturb this mass m1 here, and the other two masses m2 and m3, they remain at rest. So initially, before we saw where the middle mass m2 was disturbed and the other edge masses were at rest. Now we are disturbing one of the edge masses m1, and the middle and the third m2 and m3 are at rest. So solving the energy, momentum and frequency equations, we see the solution is again qualitatively same as the one spring two mass system with mass m and mass 2m at the ends of a spring. So the amplitude C1, C2, C3 now switch from C00 to minus c by 3, 2c by 3, 2c by 3. So in one step, m1 is moving with velocity v. It comes and collides with these two masses m2 and m3. So m1 goes back with some velocity c by 3, minus c by 3, and m2 and m3 will move forward with 2/3 of the velocity that m1 was moving. So c00 becomes minus c by 3, 2c by 3, and 2v by 3. And then it again switches to c00, and then again it switches to minus c by 3, 2c by 3, 2c by 3. So it keeps switching between these two states. So in the one state, only m1 is moving, the other two masses are at rest. And in the other state, the middle, the second and the third mass are moving with twice the velocity of the first mass in magnitude, but in opposite direction. But this solution does not work. It is not realistic. It is not realistic because it involves action at a distance. The energy momentum transfer, that is energy momentum transfer without contact, that is action at a distance. That is, if the signal has to pass from mass m1 to mass m3, it has to pass through the stress strain built up in the second spring. Without that contact, without that building up of stress strain in the second spring, m3 cannot get any disturbance. It cannot get the same oscillation as m2 as required by this solution, while the second spring remains relaxed throughout. That is, in all these steps, the second spring is always relaxed, because initially m2 and m3 had zero velocity, so it's not moving, it is relaxed. And in the second step, the solution implies that m2 and m3 should get the same exact velocity and the same kind of disturbance, 2c by 3, 2c by 3, that is the amplitude of the oscillation. It'll have same, so it will be moving in the same with the same velocity at every point in time. So there is no relative velocity between m2 and m3. So this spring 2 remains relaxed. So, but yet the spring remains relaxed, yet m3 must acquire an oscillation with amplitude 2c by 3, which is impossible. So it has to acquire this from the m1. M3 should acquire, but the spring connecting it to the rest of the masses, it's not getting any stress or strain. So it is impossible for m3 to get this energy or momentum or disturbance, any signal transfer. So this calculation does not work. It does not represent any real world phenomena. So these three set of equations that we, the energy, momentum, and frequency that we solved, these three equations are they're not representing any. The solutions are not giving any real world phenomena. So. But yet the energy and the momentum has to be conserved globally, in the global sense. So what could happen realistically when we disturb just the edge mass in the 2-spring 3-mass system? So actually what we need is, we need to drop the idea that in between two resting states there is always a relaxed state. That is, resting state is a state when the masses are at rest, all of them are with velocity 0, and all the energy and momentum in this resting state is stored within the springs. The springs are compressed or expanded or whatever, and the energy is stored as the potential energy of the springs, but there is no movement of the masses. So between two such resting states, we need not always pass through a state where all springs are relaxed. So that is not necessary that every time it switches from this all rest state to all rest state, in between all the springs have to be relaxed. That is not necessary. We have to drop that assumption, implicit assumptions that we had made. And we could also assume the frequency need not remain constant throughout. So we'll not discuss more of this here, but the frequency changes. So it can change and it will change. So the primary necessity is to conserve the energy and conserve the linear momentum, not to conserve the frequency. So energy and momentum have to be conserved at any cost globally. When all the springs are relaxed, the momentum what we calculate has to be same throughout for as long as this motion happens, and the energy at any point has to be conserved. So we need not conserve frequency or anything else. Only energy and momentum are to be conserved. And also we have to ensure that there is no action at a distance. So that is strictly forbidden. We cannot allow any solution with this action at a distance. So with that broad things, we can analyze the system. So solving the so most likely this is how the system behaves. In the first step, only M1 is disturbed. M1 starts moving right, while M2 and M3 remain at rest. The first spring is compressing from the left side. Eventually the compression stops and M1 comes to rest, because all the energy is stored in the spring, the first spring. So the most likely M1 and M2 interact with each other in an elastic collision, or in the one spring two mass kind of situation where that we had discussed earlier, and M1 tries to transfer all its energy and momentum to M2 via this first spring. Since the masses are equal, this is a possibility. So M1 transfers all its energy and mass to M2. So that is what it tries. But when M1 stops, the first spring is compressed to length L minus C and has stored all the energy. And M1 has the distance between M1 and M3 is 2L minus C at this stage. The first spring is L minus C, the second spring is relaxed L. So the total distance is 2L minus C, the total length between M1 and M3. So overall, this two spring three mass system is compressed. And at this stage, M2 is triggered into motion in the second step. M2 is triggered into motion while M1 and M3 remain at rest. So M1 comes, compresses the spring, and it transfers the whole energy and momentum to this spring first, and it stops. Now, and the spring then triggers the mass M2. So then, so M2 starts moving right. So when M2 reaches the midpoint, this is the third step. So when M2 reaches the midpoint between M1 and M3, where M1 and M3 are at rest, both the first and the second springs have length L minus C by 2 now. So both are compressed to a little extent, not L minus C by 2. So compressed by half an amplitude. Both are compressed. And the remaining energy appears as the kinetic energy of M2 with the velocity v by root 2. So this is the maximum velocity that we find for mass 2 when this is oscillating. In the first step, we saw mass 1 was moving with velocity v. But in this third step, when M1 and M3 are at rest, only M2 is moving with the maximum velocity. It has velocity only v by root 2 because rest of half the energy is stored in the springs. M2 continues moving right. So in the third step, M2 continues moving right and stops when the first spring expands to the relaxed length, and the second spring compresses to length L minus C in the fourth step. So now the compression has moved from this first spring to the second spring. So at this stage, so the compression, so between this second and the fourth step. So at this stage in step 4, mass M3 is triggered into motion. So M2 comes to stop. It compresses the spring head of it, this second spring. The first spring is relaxed, second spring is compressed, and the second mass comes to rest, triggering the third mass, M3, into motion. So M1 and M2 remain at rest. The second spring starts expanding from its length L minus C. So it is most compressed now, and it starts expanding from this compressed position, while this M3 moves right. So in the fifth step, when the second spring is also relaxed, so even this gets relaxed after some time because M3 is expanding. So L minus C becomes L. So at this stage, the first spring was already relaxed from the previous step, because M1 and M2 are at rest. So M3 is moving, it becomes from L minus C to L. So at this stage, both the springs are relaxed. They have this length L. So in the fifth step, even the second spring is relaxed, so the entire energy appears as the kinetic energy of mass M3. So M3 is now moving right with velocity v. This is the velocity that M1 had in the first step. So we see the energy and momentum has traveled from one edge, that is the left edge, to the other, that is the right edge. So it has traveled from M1 to M3 without any loss in the system. So we can note in between the steps 2 and 4, the springs do not pass through any system where both springs are relaxed simultaneously. So in this system, in this case, in this step 3, both the springs are compressed, they are not relaxed. So it is not necessary that between these two resting states 2 and 4 we should pass through a state where all springs are relaxed. So these kind of constrained oscillations may also happen. So this is a possibility. It conserves energy, momentum, or all those things. The frequency may change, but it is a valid physical process. There is no action at a distance. So it slowly transfers from M1 to M2 to M3. The energy, that's how it goes. So we can so further this signal. So this signal now, this velocity v has reached M3. Further, this signal now at the right edge of the system will travel back from M3 to M1 in a reverse fashion. So it will keep moving back and forth from M1 to it came to M3, from M3 it will go back to M1, and so on. So basically what happens is, in the fifth step, M3 is moving with velocity v. M3 continues to move right and stops when the second spring expands to length L plus C, shown in the sixth step. The distance between M1 and M3 is 2L plus C now. So the first spring is relaxed, the second spring is expanded to L plus C. The total distance between M1 and M3 is 2L plus C. Overall, the 2-spring 3-mass system is expanded, and at this stage M3 comes to rest and triggers M2, the second mass. So M2 is triggered into motion while M1 and M3 remain at rest. So M2 starts moving right. So when M2 reaches the midpoint between M1 and M3, that is in this step 7, both the first and the second springs have length L plus C2. So both the springs are in expanded state, L plus C2, L plus C2, C by 2 in this case. L plus C by 2 and L plus C by 2. So both are expanded, and the remaining energy appears as the kinetic energy of M2 with velocity v by root 2. So this is the remaining, so because half the energy is trapped in this L plus C2, C by 2, L plus C by 2, these expanded springs. The maximum velocity that M2 can have is v by root 2. That was the same that we saw in the previous step also, where both the spring were compressed. In this state, both the springs are expanded, and still the maximum velocity is v by root 2 for M2. So M2 continues moving right between step 7 and 8, and at step 8 it stops when the spring expands to the length when the first spring, so when the M2 keeps moving right, so when the first springs get expanded to length L plus C and the second spring is relaxed, at this stage M2 stops moving because the total energy is stored in this expanded spring. So first spring has expanded to length L plus C, and the second spring compresses back to length L. So this is the 8th step, and in the 9th step, basically what happens is, in the 8th step, M1 is triggered into motion. So M2 and M3, M2 comes to rest, M3 was already at rest. So M2 and M3 are at rest in step 8, and M2 triggers mass 1 into motion. So in the 9th step, even the first spring is relaxed. So the first mass starts moving right in the step 8. So by step 9, the expansion, the L plus C has got reduced to L. So in the step 9, the first spring is relaxed. Now it has, the expansion has gone and it is at the relaxed length. So the entire energy appears as the kinetic energy of mass m1. So m1 is now moving right with velocity v. So this is the same configuration as in the first step. So now it is a repetition. Only the whole spring mass system has shifted right. So now we are back to the first step. So these steps between 1 to 8, they keep repeating over and over again, and the whole system keeps moving right, translating to the right. So we see the energy and momentum has traveled from the right edge back to the left edge. In this way, the energy and momentum keep propagating or keep moving back and forth between the two edges in this non-normal mode oscillation. So this is how the whole movement looks. We have removed all the text. So this is the how. So between step 1 and step 5, the signal travels right from M1 to M3. In both the step 1 and step 5, both the springs are relaxed. Hence, the net momentum is also the same. So mv. So in between steps, they are not relaxed. Step 1 is relaxed, step 5 is relaxed. And between step 5 and step 9, the signal travels left. So initially between 1 and 5 traveled right, and between 5 and 9 it's traveling left from M3 to M1. Even in these two steps, both the springs are relaxed and we get the same momentum. So in step 9 also has the same momentum as step 1 and step 5. And overall, the first mass transfers its entire energy to the first spring and stops. The spring then triggers the second mass. The second mass shows a maximum velocity of v by root 2 because half the energy is always trapped in the springs at the least. In the minimum, half the energy is trapped in the spring. So the maximum velocity this m2 can get is v by root 2. So then the energy is energy is completely transferred to the second spring. So after this v by root 2 state, this spring 1 and the mass m2, they transfer their entire energy to spring 2. So now it is compressed and it has all the energy. Then the energy is completely transferred from spring 2 to mass m3. So from spring 1 it comes to spring 2, and spring 2 then totally transfers the energy to mass m3. So this is how it moves rightward, and then this process repeats in reverse. M3 transfers its entire energy to the second spring and stops. The second spring then triggers the second mass. The second mass shows a maximum velocity of v by root 2. Then the energy is completely transferred to the first spring, which then totally transfers back into m1. So this is how it moves left. So your momentum or energy keeps moving back and forth, so left and right. So the steps 1 and 8 keep repeating forever unless stopped, and the system keeps translating rightward. Step 9 is same as step 1 with translation. So this mechanism discussed for the 2-spring 3-mass system can be extended to any chain with arbitrary number of spring mass units. So if there is a long chain with say 10, 100, 1000, no matter how many number of spring mass units, this similar mechanism that we described for the 2-spring 3-mass system where we disturb the first mass, it will work. So in this case, the compression travels forward to the right in the first half of the cycle. So in the forward cycle, when it is moving from the first mass m1 to the last mass mn, this is the forward cycle, say. So in this first half of the cycle, this compression keeps traveling right. Whenever all these masses are at rest, in the resting state, exactly one of the springs is compressed at any step. Only one of them will be compressed, and this compression is moving rightward in the forward stroke. So this is compressed to length L minus C in the forward stroke. So this compression then hits the right edge, goes to the last mass, and comes back as an expansion. So from the last mass mn, it comes back to m1 as an expansion. So in the backstroke, when all these masses are at in the resting state, when they are at rest, exactly one of the springs is expanded to length L plus C. It is not shown here. So in this, here it's compressed, one of the springs. This is the forward. In the backward stroke, one of the springs will be expanded exactly by L plus C length. So now in the backstroke, the expansion hits the left edge, again goes forward as a compression, and keeps repeating this back and forth. So goes forward as a compression, comes back as an expansion, and goes forward again as a compression, and it keeps going on for infinity unless stopped. So the in-between masses show a maximum velocity of v by root 2, like in the two-spring 3-mass system. And the edge masses, whenever the energy reaches these edge masses, the maximum velocity becomes v meters per second for them. So in general, this may be the key for understanding the wave propagation in a spring mass system. So this may be the key. This is how the waves may be propagating in the spring mass system. So the normal modes actually correspond to stationary waves or stationary patterns where there is no energy transfer between different masses. So even if those patterns are prominently the stationary waves, they do not really explain the propagation of energy or momentum through these spring masses from one place to another place. They don't really explain. We need these non-normal modes to explain those propagation. So these non-normal modes are the ones which transfer energy from one place on the spring mass system to another place. There are very few simple, intuitive, non-normal mode configurations like those discussed in the previous slides, like this long chain with the propagation. Like that, there are very few. Maybe another simple example of this non-normal mode configuration can be seen on a chain with even number of masses. So here there are 6, 8, 10, whatever. If there are even number of masses, like this 5-spring 6-mass system, and if we disturb the 2 masses exactly in the middle, like this 3rd and the 4th mass in this chain, in this 6-mass system. So if we exactly disturb the middle masses with the same velocity v as this initial condition, then very similar mechanism discussed for this wave propagation system in the 2-spring 3-mass system with the edge disturbed. So 2-spring 3-mass system with the edge disturbance as the initial condition. So whatever we discussed for that, very similar mechanisms can be used here also to explain the evolution of this 5-spring 6-mass system. So basically the signal propagates from the center outwards towards the edges. It hits the edges and propagates back towards the center, and then again propagates out towards the edges and then travels back towards the center. So the signals in a very neat fashion, it will keep evolving, going forward and backward in this particular configuration. So, and this back and forth motion, repetitive motion, can go on forever. For most configurations, it will be either very difficult or impossible to figure out the evolution of these non-normal mode solutions. Not all these configurations may have simple solutions like this. So you can perhaps take this below configuration as a puzzle. So and find out how does this system evolve. If we say have this 3-spring 4-mass system and we disturb either the 2nd mass on the left side or the 3rd mass. So we do one of these. So and we have to, and the puzzle is to find out what happens next. How does the system evolve? Whether the signal reaches the edge masses or it doesn't reach, and how does it go about. So ultimately they have to conserve the energy and momentum, and they have to the action at a distance is forbidden. So following those guidelines, we can find actually multiple solutions for this. This is not a well-defined system. So whatever. So then how will this system evolve? So how will this system, this puzzle, this whatever the puzzle what we pose, how will this evolve? So that is a puzzle. So perhaps we might need a neat experimental setup with high-speed cameras and AI/ML, the artificial intelligence, machine learning algorithms, to resolve this puzzle, or and a similar processes in other complicated spring mass systems. So even with 4 masses, it becomes complicated, and we may need to have these high-speed cameras and machine learning algorithms to figure out what's happening in these systems and even more complicated systems. So I will end this presentation here. In the light of the discussion done here, we realize that we need to reanalyze the oscillatory vibratory systems that we have studied classically in the textbooks and so on, and also we have to revisit the wave phenomena using proper methods beyond Newtonian mechanics. Probably we need deep neophysics. Please support and collaborate with Neofizix if you are also interested in such out-of-syllabus topics. So don't use this for any marks. You won't get any marks in your university exam. But if you are interested in these out-of-syllabus topics, please join us, subscribe to our channel, collaborate with us, and support us. And so these are all beyond the scope of most normal physics courses. So anyway. Thank you. See you again.